would be the difference between a fuse map and a printed circuit, like, and what applications are they used for?
Fuse maps are only used for dealing with programmable devices. Right? A programmable device is basically a generic piece of hardware that we can customize to do whatever we want, and so you blow certain fuses to make certain connections and implement a circuit like that.
Is it like, you said programmable, does that mean like, it could be like done from the computer directly to hardware?
Yeah,
you can,
so
like, you can control like what gets connected and what not gets.
yeah, you run some software and you put in a truth table or equations or something, and then you connect a program or a physical device, usually a USB port or something, put the programmable device in a socket, run the program, and it'll configure it to implement some behavior. But that picture of a fuse map, you know, if there's 128 connections, it would be a huge picture to draw, and there's no benefit to knowing, you know, that this particular output goes to the second input of this AND gate and so on. So we use that abbreviation when we see pictures of the fuse maps, because all we're doing is saying which fuses do we blow, which lines are connected to which, right? But it's not a circuit diagram in the standard sense. So.
Yeah, I can see that.
Okay. All right, well, so after that great warm-up and entry to talking about edge trigger devices, which are like the greatest thing in the world, I have to switch gears because I have to talk about Lab 5, because Lab 4 got turned in today. So let's run quickly through Lab 5, and then we'll go back to edge trigger devices. So Lab 5, you are not doing a traffic light. So traffic light's on hold until Lab 6. So you get a break from traffic light experiments. But you're working with some circuits that will help you in Lab 6. Lab 6, you're going to add a yellow light to your intersection. So, but yellow lights need to stay on for a few seconds and then change to red and so on. So Lab 5, 3 experiments. One of them is just on paper. So first experiment is working with this chip called a 555. We've talked about this briefly. It's a different kind of chip, and it's not really digital. It's an analog chip. So it doesn't just output ones and zeros, but we're going to use it as if it's just outputting ones and zeros. So it's an 8-pin chip. From the top view, ground is on pin 1, power is on pin 8, so that's different from other chips. And we don't need to worry too much about what these other inputs mean, because we're going to get a wiring diagram for how to hook up this chip. So pin 2 and 6 get connected together. Pin 2 goes through a capacitor to ground. So capacitors are possibly a new type of component to you. They're like little, usually orange blobs with 2 wires coming out. Okay, so they're smaller than resistors usually, and sometimes it's like a little blob with 2 wires coming off like that. Sometimes it's a little blob with wires like that. Some capacitors look like resistors, but they're usually blue, and they don't have color bands on them. Some capacitors are big things. You put them in your car to keep the headlights from dimming when you play loud music. So they come in lots of different shapes and sizes. The ones in your boxes should be these little orange things with 2 legs on them. So 2 goes through a capacitor to ground, 7 goes through a resistor to 2, 7 goes through another resistor to 8, which is VCC, 4 goes directly to 8. This is just a tiny little capacitor. It's going to be the smallest one you find in your parts box, connected between ground and power. You don't really need this 1K resistor here, so leave that off. And then 3 is the output of your circuit. Okay, if you wire up your 555 like this, it will oscillate. The output, pin 3, will go between 5 volts and ground, kind of like a square wave. And the amount of time that it's high or low will depend on the values of your 2 resistors and your capacitor. Okay, so these 2 resistors is capacitor. If your resistors are in mega ohms and your capacitors are in microfarads, which is what it should be, so that's 1 microfarad, 1 mega ohm. So those are with the green bands, not the red. Then your time that the output is high and the time that it's low are given by these 2 formulas. And it'll work out to about being on for 1.5 seconds and off for a half second. So it'll be a nice slow pulsing, and if you hook an LED up to it, you should see it turn on, turn off, turn on, turn off, turn on. So things to pay attention to here. First of all, this is a funny circuit to wire up. The simpler you wire it, the better. So plan to spend some time making this thing work. Okay. And you know, 2 and 6 get connected together. Just take a nice short wire, connect 2 and 6, and you're done with that. Pin 4, it goes to pin 8. It goes through a resistor to pin 7, but it also goes to VCC because that's where pin 8 goes. So pin 4, just put a wire over to your VCC bus, and you're done with pin 4, right? Pin 8, put a wire over to VCC, and you're done. And then pin 2 is going to go to ground through a capacitor. So take your capacitor, put one end on pin 2, put the other end on your ground bus. Right? Try to build this without using a whole lot of extra connections. Right? Electrically, there's a lot of ways you can do this. But the fewer wires you use and the simpler the layout, the easier it's going to be to get it correct or to debug it if it's not quite right. And the better it's going to work. Pins 2 and 7 are connected through a resistor. Easiest way to do that, take your resistor, put one lead on pin 2, put the other lead on pin 7. So it's going to go across. Now you can have pin 2 go over here, and you can have that go over there, and you can have that go to one end of the resistor, and the other end can go over there, and that can go back there, and that can go to pin 7. But make it as simple as possible. Okay? Simplest would be one lead in pin 2, one lead in pin 7. And then same thing here, you have a resistor between pin 7 and this point up here. Well, I could go from 7 to 4, I could go from 7 to 8, but you know what? Let's just go from 7 straight to the VCC bus. Because you got your VCC bus all the way across the top. And this is one case where it's worth, on your proto board, you got 2 lines on the top and 2 lines on the bottom. And then you got all these rows of 5 lines in the middle. It's worth doing like VCC and ground on both sides. And usually there's a red and a blue, so pick something that makes sense to you. Usually red is VCC, blue or black or brown would be ground. But do something that makes sense, right? Connect one of these to your power supply, and then just put some jumpers on the other side. And there's a whole kind of style to wiring up breadboards. But in general, your circuits are going to start getting more complex now. Experiment 6 will probably be 2 breadboards. This one may be 2. You know, things like keeping your wires off to the side and so on can help. All right, so pin 8 goes to VCC. Pin 7 goes through a resistor to VCC and goes through a resistor to 2. 6 goes directly to 2. 5 does not appear anywhere. 4 goes straight to VCC. 3 is going to be your output, so that's going to go to an LED originally. 2 goes directly to 6. 2 goes through a capacitor to ground. Okay, next thing to pay attention to up here in the component ID block, or whatever this block is, pin 1 goes to ground. That's not shown in this diagram. You got to connect 1 to ground. Okay, first 2 years, 3 years that I taught this course, students and I would spend like 2 or 3 hours trying to get their 5 high 5s to work, and it would turn out pin 1 wasn't connected to ground. Because it doesn't show you in this circuit, but it shows you up here. So make sure pin 1 goes to ground. If your circuit's not working, that's going to be the first thing you want to check. Did I connect 1 to ground? Pin 5 doesn't go anywhere, that's fine. Alright, clear on how to wire that?
So we're omitting the 1K?
Yeah, leave this 1K off. Alright.
Keep going back up. So it looks like your connect, so right where the 0.01 UF is, looks like that's being connected to ground and voltage.
Right. And so capacitors, let's talk about capacitors. Capacitors don't actually conduct from one side to another. You can make a capacitor by taking 2 pieces of metal, putting them really close to each other but not letting them touch. Usually there's a piece of cardboard or something insulating in between them. So if you put 5 volts over here, and you put ground over here, no current flows. Okay, because there's no physical connection from here to here. So even though you're connecting it directly between power and ground, it's not creating a short. Okay, the funny thing that capacitors do is if I start to change the voltage over here, if this becomes a signal that changes over time, I will get current flowing. And the faster this changes, the more current will flow. But if it's just a straight DC voltage level, current flow is 0. How many people here have done Calc 1? So don't stress. But there's a differential equation describing current flow. So the current flow is basically proportional to how quickly the voltage is changing. This is just a fancy way of saying how much does the voltage wiggle around. If the voltage is totally stable, this is 0. If the voltage is wiggling 1,000,000 times a second, this is going to be really big. So the faster the voltage is changing, the more current you get. Okay, why do we want this in our circuit? Because we want a nice smooth 5 volts for VCC. But that's not reality. Reality is the voltage is always wiggling around a little bit. Sometimes it wiggles around a lot. So those wiggles will basically get shorted to ground, while the nice clean 5 volts that we want will flow through into pin 8. So it's called a de-spiking capacitor, and its purpose is to clean up the power supply. And we'll use this in 270, and it'll really be important in 270 because we'll be driving motors with our circuits, and motors produce a lot of electrical noise. If you leave that off on this circuit, it's going to work great. Okay, but you may as well put it in because it's good practice. So that's just to clean up the power supply.
We can do whatever we want for output, right?
The first thing you're going to want to do, yeah, basically, you could put it into an oscilloscope, you can hook it to an LED. Okay, I would say hook it to an LED and make sure that it's blinking on and off at some easy to notice rate. If it doesn't look like it's blinking, if it's on solidly, check your resistors. Because a lot of times you accidentally put in 1K resistors, and if you do that, it's going to blink on and off really fast, like 1,000 times a second. It's going to look like it's on. All right, so experiment 1. So build this and calculate using these formulas and the values of your resistors and your capacitor. Calculate how long the waveform should be high and low, and sketch a picture of it. Calculate and draw the clock signal based on the formulas provided. So you want to have a picture in your lab of a waveform, right? The output, how long it's low, how long it's high, show a few cycles, how long is each of those pieces, right? And label that, expected output. And then compare it to the actual output. So hook this up to an oscilloscope and get a signal trace and see how long it's high, how long it's low, and compare those two. They're going to look roughly the same, but go deeper than that. Are they exactly the same? If not, in what ways do they differ, and why might they differ? Okay, so think about reasons for the differences. So that's experiment 1. Basically hooking this thing up, getting it to output, and then looking at why it's not what you expected. All right, experiment 2. You're going to build a little flashing light thing. This is a fun circuit once you get it built. So you're going to use a 74130H, 7493, and experiment 1, which generates that output that pulses between 1 and 0. And you're going to implement an 8-light sequence. So you're going to have 8 outputs. Let's call them L0 through L7. Each of those goes to an LED. Here's the idea. First LED should light up for about 2 seconds. And then it turns off and the second LED lights up for about 2 seconds. Turns off, third one lights up, and so on until the last LED lights up for 2 seconds, turns off, and then the first one should come on again. Turns off, second one. So it just keeps alternating from one to the next. About 2 seconds for each LED, At the end of the sequence, goes back and immediately repeats. So about a 16-second total sequence. Okay, each light on for approximately 1 to 2 seconds. Given light should not be off for more than 16, so it should repeat every 16 or slightly less. LEDs must turn on in sequence as it is laid out on the proto board. So you want your LEDs sitting side by side in such a way that first, second, third, fourth, fifth, sixth, seventh, eighth, right? I don't care if they go left, right, or they go top, bottom, or they go bottom to top, or right to left, but you don't want to build your circuit, and when someone comes over to sign off on it, you say, oh yeah, so these two light up, and then this one, and then that, and this one, and that one, right? And if you don't try to lay them out in order, that's what's going to happen, because the wiring on the chips is always wonky, right? It's not necessarily in order. So put your LEDs somewhere in order and then connect to the right pins using wires. Okay, and that's just easier to do up front than changing it. So for this one, system diagram, right, with clearly identified inputs and outputs. Well, there's not really an input because you know, the 555 is generating that, but you can think of the output of that as being an input to the rest of your circuit. But it's definitely got 8 outputs, right? 8 LEDs. So write a system diagram, explain what the inputs and outputs are. And then detailed schematic, so that's wiring schematic, part numbers, pin numbers, component ID block, all of that stuff. Okay. Timing diagram, so show me the timing for all the different pieces of your circuit. Certainly at least show me the timing for the output of the 555 and the output of these 8 LEDs. Okay, so you should have a diagram that shows the output of the 555 and then L0, L1, L2, what those are going to do, right? This is going to be a big diagram because you're going to have at least these 8 outputs, and I'm going to suggest some other outputs to put in there also. And it's going to have to cover at least 16 seconds, probably at least 18, because you want these timing diagrams to go back to where at least one of these signals repeats. So it's going to be like a page by itself, right? You can put it sideways. Strongly recommend graph paper, okay, to make sure that like things are lined up and easy to follow. And then a test plan. So if you're going to demonstrate this to someone, how are they going to know if this is working or not? So you should have a description of what they should see to verify that the circuit's working. And then implement your circuit, test it, demonstrate it, get a signature. You're good to go. Good so far? We got to talk about the details of that in a moment. Let's talk about experiment 3. Experiment 3, you're going to repeat your 2-bit adder design, but you're going to use a programmable device. So redo lab 4 2-bit adder with carry using your choice of programmable device. So you need to first of all decide what device you want to use. There's a lot of programmable devices available. So there are some listed on the Clark website, the engrcs.com website. But you can go online and you can research and see what some other devices are. There's PLAs, there's PALs, there's PROMs. And you can look at different places, mouser.com, digikey.com, right? But Google gets you to everything, right? So do some research and imagine that you were going to actually build this, okay? Take a look at what devices are available, how much they cost. Are you required to buy at least 5,000 of them? Are they cheap but they're not available for 2 years, right? So do some research. There's no real right or wrong here for this part, but I want to see that you're going online, looking around at places where you could buy devices and getting an idea for like availability, cost, things like that.
So this last experiment doesn't really have much to do with sequential circuits?
So this has nothing to do with sequential circuits, and there's nothing you actually do in the lab. There's nothing you do with any parts. It's purely a paper exercise. Okay, so first part is research, picking out a programmable device. Second part, write down what functions you want to implement. So it's a 2-bit adder. It's got 4 inputs, A0, A1, B0, B1. It's got 3 outputs, some 0, some 1, some 2. Write down a function for each of those, an equation for each of those. You've already done this, so you can take whatever you came up with in your previous work. And then design a schematic using your programmable device. So that's going to have a fuse map inside. So that's going to be, you know, one line going into the AND, and you mark the connections and so on. But connect switches to the inputs, connect LEDs or something to the outputs. You don't have to connect LEDs, but you don't have to throw switches on the inputs either. Just show me the fuse map. But label everything, right? Here's A0, here's A1, here's some 2, here's some 1, right? Make sure you label the inputs and outputs. And I'm not going to give you any more specifics on that right now. I'd like you to look at that before Thursday and bring questions on Thursday. Okay? Because each of these devices is different. They have different schematics, different fuse maps, okay? But it's an exercise in actually working with whatever particular device you choose and seeing how you might hook it up to make an adder. This is your second version of a 2-bit adder. Your third one is in summer, or whenever you take 270. All right, good on experiment 3? All right, let's look at experiment 2. This is one of these times where I'm going to give you some hints. And you don't have to follow them, but they may make your life easier. So our goal is to use a 74LS138. That's a decoder. A 74LS93. That's a counter. And a 555. All right, 555 you already know about. We've talked that one. That generates an output that just toggles between 1 and 0. Let's look at the 138. All right, 74138. This is a DMUX. Takes 3 inputs in, it generates 8 outputs. And that's the 54 series, no, that's the 74 series. This is the 139 on the right, so we want the one on the left. All right, it's got 3 inputs which are called select, A, B, and C. That chooses which of the 8 outputs to activate. The outputs are Y0 through Y7. So these are going to be your 3 inputs. One of these 8 outputs is going to be selected depending on what value you put in the select. Power and ground, pins 16 and 8 as usual. 3 enable inputs. All right, so the enable is funny. G1, pin 6, is just labeled enable. That's got to be a 1. So G1 pin 6 should be a 1. G2A and G2B, pins 4 and 5, they have little circles on them. That's telling us those should be low. So G2A, which is pin 4, should be 0. And G2A pin 4 is 0. And G2B pin 5 is a 0. All right, so pin 6 is 1, pins 4 and 5 should be 0. We can tell that from the truth table. So down here, 74LS138. In order for this to do any of this interesting stuff, G1 has to be high. G2 star should be low. And it says G2 is the OR of G2A and G2B. Since we want that OR to be low, both of these, G2A and G2B, have to be low. So the truth table tells you this, but the diagram also tells you that because you've got circles here, enable is active low, no circle enables high. All right, so definitely make those 3 connections. Pin 4 and 5 low, pin 6 through a 1K resistor to 5 volts. Okay, what else does this selector do? Assuming it's enabled, so we're just looking at these lower pieces of the truth table. If your inputs are 0, 0, 0, then Y0 is low and all the other outputs are high. If your input is 0, 0, 1, like the number 1, then Y1 is low, all the other outputs are high. If your input is 1, 0, 1, like the number 5, then Y5 is low and all the other outputs are high. So this device apparently normally has all of its outputs high, but exactly one is going to be pulled low, and the one that's pulled low is determined by the inputs ABC. Now if we take these outputs and we connect them to 8 LEDs in the usual way, what's going to happen? How many LEDs are going to be on? 7 will be on and 1 will be off. And depending on the value of ABC, the one that's off will change. That's not the behavior we want, though. That's the opposite of what we want. We want 1 LED on and the other 7 off. So one option is to put each of these through an inverter. So now most of these outputs are 0 and exactly 1 will be 1. That's 8 inverters. That's another 2 chips. What's the other option? Flip the LED and connect it to power. So run your LED backwards into these outputs, connect the other end through a 1K resistor to VCC, and now what you know from your previous labs, if the output is 0, the LED will be on. If the output is high, the LED will be off. And so that's going to do exactly what you want. So that's the next trick, right? Put your LEDs backwards, save on 2 chips and a bunch of wires. Okay, well now we're almost done. If we can get ABC to be 0, the first LED will be on. If we can change it to 0, 0, 1, the second LED will be on. If we can change it to 0, 1, 0, the third LED will be on, and so on. So we need a way to somehow get ABC to count in binary. If we can somehow generate this counting pattern of 3 lines and feed that into ABC on the 138, the outputs will turn our LEDs on in the right way. So how do we generate this sequence? We use something called a binary counter. So here's the other chip you're going to look at, the 74LS93. So the one on the left is the LS90, the one on the right is the LS93. That's the one we're interested in. So this one's weird. It's got ground on pin 10 and power on pin 5. So that's one thing to pay attention to. It's got a few pins that aren't connected anywhere, 7, 6, and 4, and 13. It's got 2 inputs, input A, input B. It's got 4 outputs, Q, A, B, C, and D. And then it's got 2 inputs labeled RO1 and RO2. So let's look at the truth table. So that's LS90 on the top. Here's LS93. This table and this table. Okay, so take a look at the RO inputs in this lower right table, and it says if RO1 and RO2 are both high, the output is all low. It's not doing anything. If RO1 is low, it will count, and if RO2 is low, it will also count. So on the 7493, RO1 and RO2, go ahead and tie those both to ground. You only have to do one of them to ground, but it doesn't hurt to make them both low. Yeah?
What do you mean by count? What's different?
So what this device is going to do is going to count in binary for you.
Does it like count up?
It's going to count up. Yeah, we probably should have looked at that first. Each of these monolithic counters contains 4 master-slave flip-flops, gating, blah, 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 blah. Doesn't really tell you. So binary counters typically count up, right? Unless it's called an up-down counter or a down counter. Up-downs can go up or down, downs go down. So this is going to give us a nice sequence of bits that look like it's counting in binary. So first thing is you have to set these reset inputs to be low. Okay, and now each time that it counts, your output, which looks like QA, QB, QC, QD, is going to bump up in binary. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. It says C note C, and note C says output QA is connected to input B, and this is where things get ugly. So I'm going to suggest you ignore these notes and you ignore what your really good friend who got their lab working tells you, or your friend who took this course before. Well, you don't have to ignore it, but I will offer you an alternative. If you're making a 4-bit counter, this is what you need to do. You need to feed your input into pin 14, and you need to take your output QA and you need to connect that to input B, which gives you output QB, QC, QD, and so on. Okay, so here's how I'm going to suggest you use this. Ignore input A, ignore QA. Because this can function as a 4-bit counter, but you only need 3 bits. So here's one way to do this. Take your 555 output, put that to the 74 LS93 input B, and then take your counter output from QD, QC, and QB. And QD is going to be your most significant bit. QB will be your least significant bit. Because internally this is a 3-bit counter. And input A goes into a 1-bit counter. And if you want a 4-bit counter, you need to take this output QA and connect it to input B. And that's what this node is up here. Node C, output QA is connected to input B. But the easiest thing to do is just ignore input A, ignore output QA. Feed your 555 into input B and take your output of your 3-bit counter from here, QB, QC, QD. So you connect that to A on your 138, connect that to B on your 138, connect that to C on your 138. So that's my final suggestion. 555 output pin 3 goes to input B on the 93, and then you read the output of your counter off QD, QC, and QB. And these go to the 74 LS 138. So what's the whole setup here? You got a 555 timer. It's generating pulses every 2 seconds. That's feeding the input of this clock circuit, right? Input B. So every 2 seconds, this counter counts, and you take the 3 bits that are coming out of the counter and you feed that into your 74 138. And as those inputs change from one count to the next, your 8 output values change. One of them goes low, and then the next, and the next. And those are going into your backwards LEDs, so it lights up one LED at a time. Okay, you can squeeze this on one proto board if you're really good about it. A lot of times it ends up taking 2 boards. Not a problem either way. But you really want to kind of think about this and test it as you develop it. Don't build a circuit with, 6 chips and 100 wires and plug power in and it doesn't work. What do you do from there, right? It's a really easy circuit to test as you go. So the timer you're going to test by itself already, right? So throw an LED on there. Keep the LED there. It lets you know that it's blinking. It makes you feel good. Something's happening. That's all good stuff. Connect the 555 to the input of the counter. And I would take the time, take 3 LEDs, hook them up right here. Put them side by side, put QB on the right, put QD on the left, put this one in the middle. And when you run your circuit, you should see those 3 LEDs counting in binary. If they're not, don't bother with the 74138 yet. Right? You're going to be feeding in a signal that's not doing the right thing. The output's not going to be doing the right thing. So play around with the timer and the counter and get this output to be nice and clean, what you exactly expect. All LEDs off, first LED on, second one on, first one off, both 2 on, so on and so forth. And then when that's working, hook that up to the 74138 and see if you can get the whole sequence of LEDs to count. Does that make sense? So you want clean wiring diagrams on this. When you make a wiring diagram with a timer, you don't have to draw a picture of the chip, but symbolically, right, you might want something like this. So your 555 you're going to have a schematic for, so this is going to go to ground and this is going to go through a resistor and capacitor and so on. And here's pin 3 coming out. So that's going to be a wiring diagram. You got to draw that. But then here I would just do something like 74LS93 and label this input B if that's what you're connecting to. And put down the pin number. I don't know what pin number it is. I'll put 12 with a question mark. Right? But put both things down. Tell me what input you're going into and then put the pin number on it. Right? And this is going to be, like U2. And that's specified up in the component ID block. But you don't need to draw this picture 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and go over to the correct spot, right? You can put this however makes sense. So it's kind of like a really fancy gate, but it's not a standard gate like an AND or an OR. So label what the inputs do where they are. If this is QD, QC, QB, and whatever the pin numbers are on those. And then same thing for the 74LS138. So maybe that's A and maybe that's B and whatever. Does that make sense? All right, so the cleaner your diagrams and the more you develop this in steps, the easier it's going to be to get your final circuit working. All right, any questions on that?
So what does a capacitor actually do?
Oh, in general?
Yeah.
Capacitors store charge, basically. I mean, they do calculus. They measure how quickly a voltage is changing, right, which is what a derivative is. But the main thing we do with capacitors is we use them to store a charge. And if the voltage is changing, it will load charge into the capacitor instead of running it through. So we can use them to de-spike circuits. You can make a really simple tone control on an amplifier, because if you short 2 lines going to a speaker, any high frequencies are going to get shorted from here to here. They're not going to come out, so you're going to bring out the bass. If you put it in series, any low frequencies are going to get blocked, and the high frequencies are going to come through, so it's like turning up the treble. So when I was a kid, my dad made me a little speaker system and had like basic tone control just using a few capacitors. It was like really exciting. And you use them, in cars, your headlights tend to blink out whenever the bass thumps, right? So you put a capacitor in the headlight system and it will store extra charge, and when your bass hits and your speakers pull a lot of current to move the woofer to push a lot of air, the extra current that your headlights need comes from this big capacitor, and your headlights stay lit. And so you can find giant Farad-sized capacitors. There's a cool one called the Raptor. It's got like a T-Rex on the front or something. You can find these things to put into your sound system in your car. And if you do the engineering sequence 204, 252, 253, you find lots of other things you do with capacitors. And they all kind of like build off of this fact that they do calculus, along with inductors, which do something opposite. All right, we got enough time to start edge-triggered devices. So what we've been working with so far, we've been calling latches. When we move to being edge-triggered, instead of paying attention to the level of an input, we're going to have what's called a flip-flop. And flip-flops are named flip-flops because, well, there's lots of urban myth, but apparently the early circuits, they actually made kind of a flip-flop sound, like when you walk in flip-flops. But who knows? So here's the idea. We're going to take a pair of latches. I'm going to make what's called a master-slave configuration. So here's a load input, here's a load input. And we're going to put these into what looks like a big circuit. And I may have messed this up already. I think that looks good. So we got two plain old D latches, level triggered devices inside here. We have the output of the first one feeding the input of the second. Our flip-flop has an input D over here on the left, which feeds the first latch. It has an output Q, which comes from the second latch. And then it has an input that we're going to call clock. All right, so three possibilities here. Suppose that the clock is equal to 0, it's low. So in that case, this load input on this latch is low, so this is stable. Nothing is changing on Q here. Okay, that clock is 0, gets inverted to a 1. This load input is a 1. So this is a 0, this is a 1. Which means whatever comes in this D input is appearing on the Q output, which is coming out of our final Q. But since this load input is a 0, this Q is not changing. So D is not changing, so this Q is not changing. So this is rock solid stable. You can change this D input over here up and down 1,000,000 times. Q is not going to change at all. Okay, now suppose our clock changes to a 1. This is going to become a 1. This is going to become a 0. Well, when this rises from a 0 to a 1, now you've got a 1 going into the load. Whatever the D input is here, that's going to come into this latch. That's going to appear on Q. So now this output is changing. Whatever D does, we see on this internal Q output. But since clock is 1, this load line is 0, so this output Q is still not changing. It's totally stuck at whatever value it was, because this is ignoring its D input. But whatever D input we have over here is now appearing on the output of that first latch. So the clock's equal to 1, nothing is changing yet. Okay, now the clock drops. So at that moment where the clock drops, this becomes a 0, this becomes a 1. At that moment, whatever value we had on D, at that exact moment where the clock drops, now gets loaded into here, because the load line went from a 1 to a 0. That's just our plain old D latch. But whatever that value is, which has been coming out on Q, now, since this latch has a load input of 1, that D value is going to get sent to its output. And now Q is going to change. So at this moment, where the clock drops from 1 to 0, whatever value we have on D, that's going to get sent to the Q output. And now, while the clock remains low, D can start changing some more, and it's not going to come through here, and so it's not going to affect Q. So the only time Q ever changes is when the clock drops from 1 to 0. And at that point, whatever value you have on D, that's what Q becomes. So this has a much nicer timing diagram. And let's suppose Q starts off at 0. At the moment when the clock drops, it looks at the value of D. It's a 1, Q is going to be a 1. So all of this noise on the input is completely ignored on the output side. And it only pays attention to the input when that clock drops from a 1 to a 0. So this is what's called a negative edge triggered device. Negative edge means clock changes from 1 to 0. If we put an inverter here instead of here, this will be a positive edge triggered, and it will only pay attention to the clock when the clock rises. But if we use this kind of device in our x equals x plus 1 circuit, it's going to work perfectly. Every time that the clock drops in this case, the value of x plus 1 will get loaded into our x register, and that's it. It's not going to race back around and load x plus 2 or x plus 3 until the clock rises again and then drops again. So the sense is, when the clock rises, your input gets this far, and then when the clock drops, it gets all the way to the output. And at that point, inputs can only go this far, right? And then when it rises, it gets loaded into here, goes out there, and it follows through.
So the clock needs to be 0 twice for the output to fully.
Clock needs to drop. Yeah. So effectively, it needs to be 0 twice. Okay, so this is called a D flip-flop. And so I try to use the convention that gate means that it's level triggered, flip-flop means it's edge triggered. And pretty much everything we do other than random homework questions, we're going to deal with flip-flops from here on out, because they have this nice clock behavior. All right, so we'll talk about a few other kinds of flip-flops: RS flip-flops, JK flip-flops, and T flip-flops, and then we'll start building state machines with these. We'll start analyzing state machines. All right, so I will see you Thursday.